Hey everyone, let's practice some exponential growth modeling. Pretty standard population growth problem, right? We are given two points, right? A year and a population, and we need to use that data to come up with an exponential model and find when the population equals a certain amount. So as always, our approach is going to be to build a general model and then solve, in this case for t. But let's let t equal the number of years post 1950. And so then P of t equals the population at time t in millions. Right? Because I don't want to write comma 0, 0, 0, comma 0, 0, 0 every time. Okay, so we have that P of 0 equals 2560, and P of 10 equals, I guess, 3040, right? So to build the model P of t, we go with that second point, combine it with the equation that we know. All right, whoops, I think I forgot an e to the 10k equals 3040. You can do a little bit of division. You can keep it as 3040 divided by 2560, but it does reduce a bit nicely. 16 actually goes into both of them, and you get 19/16. So let's just do that. It's less writing, easier to look at, right? And then you can solve for k, right? You take the ln on both sides. I guess I will do that really quickly. Right, so you get that k equals 1/10 ln of 19/16. Okay? So this is great because now we have a model for P of t. Let's write that down a little further. E to the 1/10 ln of 19/16, right, t. Not the loveliest looking thing in the world. Not the loveliest looking thing in the world, but still, yeah, it's fine. So now we want to let P of t equal 4,000, right? Because we want to find when the population reaches 4,000 million or 4 billion, okay? So we're going to let P of t equal, well, on the one hand, it's going to be this again. On the other hand, we'll let that equal 4,000. Divide that by 256, and it's worth asking whether 16 goes into that nicely. Let's just see, right? This will imply that e to the 1/10 ln of all this, 19/16 t, equals, let's see, 400 over 256. Is 16 go in nicely? This goes in twice. A5. 250? Yeah, that seems about right. So we get, actually, I think even 32 goes into this nicely. We won't worry about it right now. We'll just say that we get, I think it's 250. 250 divided by 16. You can actually reduce that even more. Factor of 4, 6. No, maybe just by a factor of 2. Right, maybe you can make that 125 over 8. I believe that's true. I believe I got that ratio correct. So anyway, just do that. You don't need to simplify that, but I think it's just a little bit nicer to look at. Anyway, you're going to get 1/10 ln of this equals ln of that. And so we're going to get our answer that t equals 10 ln of this divided by ln of that. Okay. All right, and so for your exam, I'm going to leave it like this because for your exam, this would be a correct answer. Really what we should do is we should go into Google or Desmos or something, calculate this out, and then add it to 1950. Okay. One thing also to point out is that this is a more accurate model than this one that we did in class, which makes sense because it's later. We have more accurate data later on. Okay. Next up, radioactive decay. Let's save that for another video because it is, after all, decay.